Okay, so tonight we're going to be doing a review session for chapters 17 thermochemistry and chapter 18 electrochemistry, which is what your multiple choice exam on Friday is on. So we're going to start out just by reviewing the challenge problems from Monday's session. Okay, so the first two questions were both kind of theoretical understanding questions. So the first one asks, which of the following statements correctly describes the use of the Nernst equation? So A says it is used to calculate cell potential with changing concentration of reactants and products. And so that statement is true, and I'll, on the next slide, kind of explain why, but A is true. B says it will be used to calculate cell potential at temperatures other than 25 degrees Celsius. That statement is also true. And C, it says it is used to calculate cell potential at equilibrium. And that is false. That is not our Nernst equation. And so the answer to this should have been D. Both choices A and B are true. Okay, so A talked about using the Nernst equation whenever our concentration of reactants and products are changing. Right, so remember that our concentration or pressures of reactants and products are changing in order to establish equilibrium, right? They want to reach equilibrium. And once they reach equilibrium, they don't really change. They stay the same. And so if our concentrations are changing, this implies that we're at Q, right? It's basically saying we're not at equilibrium. Okay, so if we're at Q, our reactant or reaction quotient, right, we're gonna have to plug Q into our Nernst equation. So if you're not familiar with Nernst equation, it's written at the bottom. It's this one, cell potential equals our standard cell potential minus RT over NF times the natural log of Q, our reaction quotient. Okay, and so again, if we're changing our concentration of reactants and products, this is implying that we're at Q, and the only equation that we have that includes Q is our Nernst equation. Okay. B was also said to be true, right, at temperatures other than 25 degrees Celsius. And the reason for this is really 100% of the time, or at least 99% of the time, if not 100. But as far as I'm concerned, E naught, our standard cell potential, is always calculated at 25 degrees Celsius, right? So if you're plugging in to solve for E naught, you're going to be solving for that at 25 degrees Celsius, or you're going to solve for it from that table of your reduction potentials, which are all measured again at 25 degrees Celsius. And so really any time that you're not at 25 degrees Celsius, you're going to be utilizing your Nernst equation. And that'll account for how temperature affects your cell potential. Okay, both A and B were listed as times to utilize the Nernst equation in Monday's session. Now, C is not true. Okay, at equilibrium, we will not be using the Nernst equation. Instead, we'll be using kind of a derivative of the Nernst equation, which is this equation. E naught equals RT over NF times the natural log of K, or equilibrium constant. Okay, so we'll be using this equation, not our Nernst equation. And the reason for this is if you actually plugged in all your values into the Nernst equation at equilibrium, you'd actually find that your cell potential E is 0 at equilibrium always. And so there's really no need to use the Nernst equation because you already know your cell potential is going to be 0. A more useful equation is solving for your standard cell potential, E naught, which you'd use through this equation. Okay, and as always, before I kind of continue on to this next question, especially in the review sessions, please feel free to ask questions at any point. I'm sure if you've been watching SI videos for a while now, you'll kind of notice that if you do type a question to the chat, I will get to it. However, I tend to do it when I kind of have the ability to answer the question. as I don't do the best job of answering when I'm reading and trying to explain something else, so on and so forth. However, if I'm explaining something and it doesn't make sense and you want me to kind of talk about it a little bit in more detail in that current moment, I always recommend people unmute your microphone and ask if you have the ability to do so. As I don't know, it's a little bit easier to answer questions fully and completely when we're able to have some dialogue back and forth. Okay, so number 2 asks which of the following statements is true? And I kind of wrote the options incorrectly. I meant for D to write at equilibrium, the standard cell potential of a cell is 0, which would have made that statement false. However, how I have it written, statement D would be true. And I'll get to it, statements A and C are also correct. Okay, so in this instance, A, C, and D should have all been correct. Only B would have been incorrect. Okay, so the actual choice wouldn't have been here, but how it's written on this slide, I think the best choice would have been A, C, and D. Again, I didn't mean to write D in this way, but that's how it kind of came out. Okay, so looking at A voltaic cell has a negative Gibbs free energy change. So remember that a voltaic cell is an electrochemical cell that's spontaneous, right? So it has a positive E value. Okay, now if we know that that cell is spontaneous, right, what would the Gibbs free energy change have to be? Well, a spontaneous change in Gibbs free energy is associated with a negative delta G value. Okay, so a voltaic or galvanic cell, which are our spontaneous electrochemical cells, they will always have a negative delta G value. Okay, so statement A would have been correct. Okay, statement B is incorrect. So it says in electrochemistry, reduction potentials are always negative, while oxidation potentials are always positive. And so if you just look at a chart of, you know, all your reduction potentials and all of those half reactions, you'll notice that there are plenty of those half reactions and plenty of those reduction potentials that are both positive and negative. Okay, so just kind of looking at a chart, you'd be able to realize that this isn't true. I just kind of threw around some jargon that might make it a little bit confusing. Okay. C says half reactions with more negative reduction potentials make better reducing agents. Okay, now this is really important for this statement to understand your terminology. Okay, so reducing agents, remember that reducing agents get oxidized. Okay, so when you're looking at your reduction potentials, right, if something's getting oxidized, you actually have to flip that half reaction and change the sign associated with the reduction potential. Okay, so if you have a very large negative reduction potential and you want to oxidize that half reaction, right, remember reducing agents are oxidized. If you want to oxidize that half reaction, your potential, which is now an oxidation potential, is going to be a large positive number, okay, which actually favors the reaction, right? It'll help the reaction be spontaneous. And so C is actually true. Okay, and one way, if you didn't quite follow me on the logic behind that, definitely feel free to ask me to clarify a little bit further. I also have it written out on the next slide. But Dr. P shows those charts of all those reduction potentials, and you can see the trends that as you go towards more positive reduction values, you will have stronger oxidizing agents. However, as your reduction potentials get more negative, those half reactions are better reducing agents. Okay, so statement C should have been true. In statement D, at equilibrium, cell potential will be 0. So that would also be true. Okay, so I'll just kind of give you a minute to read this, and I'll just kind of clarify points C and D a little bit further. Okay, so again for C, reducing agents by definition get oxidized, right? They do the reducing to a different compound by getting oxidized. Okay, and so if they're getting oxidized and their reduction potential is negative, right? If they're being oxidized, we have to actually flip the equation, which means your oxidation potential will be a large positive number, which will cause the reaction to be spontaneous, right? Those really large negative reduction potentials like to be oxidized. They preferentially want to be oxidized because that helps yield a spontaneous reaction. Okay, and then again, D is actually true. E, the cell potential, not standard cell potential, but just cell potential at equilibrium will be equal to 0. And you can actually use this by using or prove this using the Nernst equation, right? So here's the Nernst equation, and E naught, right, equals RT over NF times the natural log of K. Now, if we're at equilibrium, Q and K are equal to one another, okay? And so if we actually plug in this equation for E naught into our Nernst equation, right, we'll pretty much see that we have some variables or some numbers to minus itself, right? So it doesn't matter what these numbers are, you're basically taking some number and subtracting from it itself. Therefore, E will always be 0 at equilibrium. Okay, are there any questions before moving on? Okay, if there are no questions, we'll go on to the next question, which is actually kind of 3 questions in one, right? So we're going to use this same setup for questions 3, 4, and 5. So we're told we have a galvanic cell, and it has 2 reactions occurring within it. There's a manganese reaction, and there's an aluminum reaction. And so question 3 asks for the proper notation of this cell. Question 4 will ask for the cell or standard cell potential of this reaction or this cell. And then question 5 will ask for the change in Gibbs free energy. Okay, so one thing that I'll kind of apologize for is if this notation kind of messed you up. I was kind of having a hard time formatting it, but the commas were supposed to represent kind of like single lines, while the semicolons were supposed to kind of represent the double lines, kind of separating anode from cathode. Okay. And so the big key to this problem, or the big hint, is they tell you that this is a galvanic cell. Okay, that's a really important point, because by definition, a galvanic cell has a positive cell potential, or a positive E value. Okay, so let me go back to the half reactions real quickly. Okay, so we're going to want to flip one of these 2 half reactions. Okay, and when we flip one of the half reactions, we're going to change the sign on E naught, right? And so we want to ask ourselves, which one of these numbers should we change the sign to so that when we add them together, we get a positive number? Okay, so that leads me to recognize that it's going to be the aluminum equation that we need to flip. Okay, so as you can see, I just rewrite my manganese equation. So manganese is going to be reduced to manganese solid. Its reduction potential is negative 1.182 volts. And then you'll notice that I multiply it by 3. Okay, now we'll come back to this and why that's important in problem 5. So in a couple problems from now. But what I want you to notice is even though I multiply this half reaction by 3, my reduction potential does not change, right? It's still negative 1.18 or so. Okay, now my aluminum equation, you'll notice I actually flipped. Okay, so now its aluminum solid is oxidized into aluminum 3+, which reacts with 3 electrons. And so now I'm going to write my E naught in terms of oxidation. Okay, and so to write it in terms of oxidation, I just changed the sign of it. Okay, so my oxidation potential of this aluminum half reaction is 1.68 volts. Okay, and then to this aluminum equation, I multiplied the whole thing by 2. But again, notice that did not change my oxidation potential. Okay, now before moving on, the reason why I multiplied these half reactions by certain coefficients is because I want my number of electrons transferred in each of these half reactions to be the same. Okay, and so it is really important that you do that. Okay, so as you'll notice, I multiplied the manganese half reaction by 3 so that there were 6 electrons transferred, and I multiplied the aluminum equation by 2 so that it also transferred 6 electrons. And again, that's going to play a really important role in question number 5. Okay, now once I've manipulated my half reactions, I add them together, and so my overall equation is 3 manganese 2 plus aqueous plus 2 aluminum solids go to 3 manganese solid molecules plus 2 aluminum 3 plus aqueous atoms. Okay, and so from this equation, I can pretty easily see that my manganese from reactant to product side is being reduced, while my aluminum is going to be oxidized. Okay, and so remember that reduction happens at the, I forgot an E, but happens at the cathode, while oxidation happens at the anode, right? It's not the best way to remember it, but how I remember it is that oxidized and anode begin with a vowel, cathode, the C in cathode, and R in reduced. What they start with starts with a consonant. Again, I don't love that that's how I remember it, but that has helped me. So if you keep getting them confused, that is one potential way that might help you remember that. Okay, so the actual question asks, what's the standard notation? And so remember that when we write standard notation, we are going to write our anode first, then draw a double line, and then write our cathode. Okay, and these single lines separate phases. Okay, and so most of the time, not always, okay, but most of the time, the single line will separate reactants on the left from products on the right. Okay, this doesn't always happen, especially if your reactants and products are in the same phase. So if they're both in the aqueous phase, I went over on Monday how you write that specific notation. But most of the time, your reactant and product are in different phases. So for example, solid and aqueous here. And so you separate them with a single line. And so aluminum solid, aluminum 3 plus aqueous, double line to indicate that after it's going to be our cathode. And then for our cathode portion, we do our reactant manganese 2 plus goes to manganese solid. Okay, so the answer should have been C for that. Okay, 4, again, what's the standard cell potential for the cell? And 5, what is the standard change in Gibbs free energy? Okay. And so 4, we really did all the hard work for 4 already, right? We already, and let me go back 2 slides, we already manipulated our 2 half reactions. So once we get our half reactions in terms of reduction and oxidation, you'll see that we added these reactions together to get our overall equation. And so to find our standard cell potential for this overall reaction, we're just going to add our cell potentials together. Okay, and so all we have to do here is add negative 1.182 volts plus positive 1.68 volts. And so this gives us a cell potential of 0.498 volts. Okay, and so that corresponded with choice D. Okay, now before moving on to part 5 or question 5, I just want to show you something about our answer choices. Right, in part 4, we can see that the cell potential for the cell is a positive number, meaning this is a spontaneous, right, it's a galvanic spontaneous cell. Okay, so if this is a spontaneous cell, we should know that the Gibbs free energy change should be negative, right? Because negative changes in Gibbs free energy also correspond with spontaneous reactions. Okay, so knowing that this was a galvanic cell right off the bat, we should have been able to eliminate for question 4, choices A, B, and C, because those have negative potentials, which are not a galvanic cell. And after we proved in question 4 that this was a galvanic cell with a positive cell potential, a positive E value, we should automatically be able to eliminate choices D, E, and F from question 5, because we know that we should get a negative change in Gibbs free energy. And if we didn't, it's going to be a calculator error, right? If you have a positive E value, you should always get a negative delta G value. Okay, so our equation to find the change in standard Gibbs free energy is delta G naught equals negative N times F times our standard cell potential. So we found above that our standard cell potential is 0.498 volts. F is Faraday's constant. It's always going to be 9.648 times 10 to the fourth joules per mole volts. And then N represents the number of electrons that are transferred in this redox reaction. And so that's why it was really important to make sure the number of electrons transferred in each half reaction matched. Okay, because if they don't match, you might input the wrong number for N. Okay, and so those number of electrons matched when they each equaled 6. And so that's what we're going to input for N here. From there, we just multiply the numbers together, and we find that delta G naught is approximately negative 288 kilojoules, which was answer choice A. Okay. Now the last challenge problem we're going to go through, we'll notice that we actually skipped number 6. That covered some material we weren't able to get to on Monday. And so we skipped right to question 7. Now there was a slight error on this problem. I said that it was a voltaic cell. However, that would not be correct. This is actually an electrolytic cell. However, that one detail shouldn't have really thrown off your math. It's just I technically used the wrong name there. Okay, but in this circumstance, this is a Nernst problem, Nernst equation. So here, the equilibrium constant at 25 degrees Celsius is 0.213, and this occurs in an electrolytic cell that transfers 3 electrons. Okay, now this experiment is going to be carried out at 60 degrees Celsius, and the reaction quotient, or Q, is found to be 0.337. And it's saying, what is the cell potential? Okay, so I started out just by writing some of my key pieces of information, right? I wrote my equilibrium constant at 25 degrees Celsius, and I was told that 3 electrons were transferred during this reaction. That comment is an indicator that N is equal to 3, right? The number of electrons being transferred is 3. Okay, now we calculate our standard cell potential at 25 degrees Celsius and at equilibrium. And so I'm going to use this equation to solve for my standard cell potential. Okay, now because we're at 25 degrees Celsius, you may have noticed that in SI and also in lecture, they showed you a slightly alternative equation that really just multiplies R times T and divides it by F. And it's this value, right? 0.0257 V. That's going to be divided by N, and you multiply it by the natural log of K. Now, you can only use this when you're at 25 degrees Celsius. Okay, but again, it's equivalent just to plugging in R, F, and T at 25 degrees Celsius. Okay, so I'm just going to use this slightly more simplified version. Okay, so above, I found out that N should be equal to 3, which is the number of electrons transferred, and I plug in my equilibrium constant. So this tells me that at 25 degrees Celsius, which is where our standard cell potential is calculated, or the temperature it's calculated at, my standard cell potential is negative 0.0132 volts. Okay, and so now I'm going to use this value and plug it into my Nernst equation. Okay, so the Nernst equation is going to allow me to solve my actual cell potential at non-standard conditions. Okay, so my real cell potential, E, is going to be equal to my standard cell potential, which we solved for above, minus R times T divided by N times F times the natural log of Q. Okay, so I'm going to plug in my E naught value that we solved for above. We're going to subtract from it R, which is a constant, 8.31 joules per mole K, times our temperature, which is 273 plus 60 degrees Celsius, right? We're just converting that to Kelvin, divided by N, which is still going to be 3, the number of electrons transferred. And N is going to be multiplied by Faraday's constant, and this whole portion is going to be multiplied by the natural log of Q, or reaction quotient. Okay, from here, it's a bunch of algebraic manipulation and kind of just, solving for our variable. And what we'd find is that our actual cell potential would have come out to negative 0.0028, which is approximately negative 0.003, which was answer choice D. Okay, I didn't see anything pop into the chat, but are there any questions up to this point? And I typically like to do this little transition by saying, if you don't have any questions, please just sign in at this point in the chat using your net ID. And once pretty much everyone's signed in, I'll kind of know that there are no lingering questions and we can start on the review portion. Okay, so I think most, if not everybody, has signed in into the chat. So just in case a couple of people are typing a question, these are the main topics from chapter 17 that we'll be going over, right? So this is our thermochemistry chapter. So we're going to start talking about enthalpy, delta H, then followed by our entropy conversations, so delta S, before moving into our laws of thermodynamics and Gibbs free energy. And then we'll end by talking about pressure in its relation to free energy along with equilibrium. Okay, so again, some of this stuff will be new, but for the most part, I kind of recycle and use the parts that I like best. So most of this you will have seen before in the exact same way I'm presenting it. So enthalpy, or delta H, I'm not really going to talk much about because this was actually a topic from last semester. But realize that it's just the difference in bond energies between reactants and products. And this is calculated at a constant pressure. Okay, they always do this at a constant pressure. Now we really, unless it's given to us, really the only way we can calculate delta H is through this equation, right? So we're going to add up the enthalpy of our products. So we're going to take the sum of that. And from that, we are going to subtract the sum of the enthalpy of our reactants. Okay, and so in order to do this, if they wanted you to calculate this, they would give you a big table of values. And if you ever felt like you didn't have enough values to calculate delta H, remember that elements in their standard states have an enthalpy value of 0. So they would not appear in the chart. Okay, so a good example of this would be O2 gas, right? Diatomic gaseous oxygen. That's its natural state, and therefore its enthalpy value would be 0. Okay, solid carbon, that's its natural state. Its enthalpy value would be 0. Okay, and just some key terminology to remember with enthalpy is if you ever have a negative delta H or change in enthalpy, that is an exothermic reaction, right? That means your system is releasing heat energy or energy into the surroundings. And if you have a positive delta H, that's an endothermic reaction. That means that your system, what you focus on, is absorbing or taking heat or thermal energy from the surroundings. Okay, and again, just something I want to emphasize is that these pieces of terminology are always in reference to the system, okay, which is typically a reaction occurring. Okay, now in this chapter, we tend to have a larger emphasis on entropy, which we denote with S or delta S. Okay, this was new this chapter. Now, entropy is the measure of molecular disorder. Okay, and so spontaneous reactions tend to shift towards increased disorder, right? So positive delta S is what we tend to see reactions go towards because that helps the reaction become spontaneous. Okay. Now, entropy as a whole is based on the number of arrangements or microstates that molecules can have. And I believe this chapter was taught by Dr. S, and he went through in one of his lecture videos the concept of positional probability. And basically, positional probability is looking at all the possible states that molecules can undergo or be in. And you'll notice that the natural state, or the state of highest disorder, is the one that has the highest positional probability, right? It has the highest chance of occurring is what we'll see. Okay, now something I think that might have a little bit more relation to what you'll see on the exam. You could see positional probability, but I think these trends are very, very important for you guys to know for the exam. And I believe Dr. S gave many, many examples that kind of had you practice these general trends. Okay, so these are about 5 trends that I would recommend knowing. Okay, so entropy tends to, or it increases with increased temperature. Okay, so really every degrees Celsius that you increase, or really any fraction of a degrees, you will theoretically have an increase in your entropy. Okay, and that's just because the amount of heat energy from the environment will allow greater molecular movement. Okay, and we can kind of see this on a macro scale when we look at our next trend, right? This next trend is really similar to the first trend. It's just on a more macro scale, right? Entropy increases as we go from a solid to a liquid to a gas, which, as we know, occurs as we increase the temperature. Okay, and I think this second one's a little bit easier to understand, because as you go from a solid to a liquid to a gas, your particles physically have more freedom, right? Think of a solid ice cube. Your water molecules are extremely densely packed, and the only movement that they have might be rotation or slight bumping into each other, right? In a solid, you don't have much movement. But as that ice cube melts and becomes liquid, right, liquid water flows, right? The molecules can kind of go really anywhere within the liquid, right? They do have a fixed volume, but within that volume, they can go where they please. Now, gases have the highest entropy, right? They're floating around, they're bouncing off everything. They have a large amount of disorder. Okay, so gases have the highest amount of entropy. Now, if you're ever asked to compare reactants versus products and their entropies, right, the entropy is almost always greater on the side of the equation with more moles of gas, right? So again, we learned above that gases have the greatest amount of entropy. And so 2 moles of gas is just going to have greater disorder than 1 mole of gas, because if you have multiple moles of gas, there's just going to be greater amounts of collisions, greater amounts of reactions taking place, more volume occupied, etc. Okay. Now, if you're ever comparing reactants and products and their entropies, and you have the same number of moles of gas on each side, the side with the more complex gas will have greater entropy. So, so typically you'll see this where one side of the reaction has gases in their natural state, like H2 gas, O2 gas, etc. And on the other side, the gas will be a compound, right? So it'll be a combination of atoms in the gaseous phase. Okay, so whenever that occurs, if there are the same number of moles of gas on each side, you'd go for the gas that's a compound. Okay, that would tend to have greater entropy. Okay, the fourth trend to note is that entropy will increase as the volume increases. Okay, so anytime the volume increases, our entropy is going to increase. And because of the relationship between volume and pressure, this means that entropy will increase anytime our pressure decreases, right? Because a decrease in pressure is associated with an increase in volume. Okay, and the last trend is when solutes are dissolved in solution, right? So when a solid is added to a solution and it splits into its respective ions, ions with lower charges tend to have higher entropy values. Now, something to note here is this doesn't mean that the change in entropy, the delta S, will be positive, right? It does not mean that it'll be positive. It just means that if you have a solid that splits into ions with positive and negative 1 charges versus a solid that splits into positive and negative 2 charges, so positive 2 ion, negative 2 ion, the solid that split into the plus and minus 1 charges would be expected to have a more positive delta S value compared to the solid with positive or negative 2 charge. Okay, and this last trend is pretty complex, right? For the most part, solids dissolving in water. I don't think they would really ask you, is this positive or negative delta S? The trend that they'd be looking for is realizing that the smaller the charge, it'll likely have a more positive delta S value. Okay, it still could be negative, but more positive. Okay, I'm just going to quickly touch upon our 3 laws of thermodynamics covered. So the first law of thermodynamics is that the energy in the universe is conserved, right? We have conservation of energy, and it can be transformed from one form to another, but no energy is created or destroyed. Okay. The second law of thermodynamics plays kind of a larger role in this chapter. It says that spontaneous reactions always have an increase in entropy for the universe. Okay, and so spontaneous reactions will always increase the entropy of the universe. Okay, but we have this equation that the change in entropy of the universe is equal to the change in entropy of the system and the change in entropy of the surroundings. Okay, so just because our system, maybe the reaction taking place, maybe it will have a decrease in entropy, but that doesn't mean that the universe couldn't increase in entropy, because again, it's dependent on not just the system, but also the surroundings entropy. Okay, and then the last law of thermodynamics is entropy of a perfect crystal at 0 Kelvin is 0. And really, this is kind of the basis as to where we get our S naught values that allow us to solve for our change in entropy. Because I apologize, I actually forgot that equation, right? Remember that delta S equals the sum of entropy of our products minus the sum of entropy of our reactants, right? It's actually the same equation as enthalpy, it's just with S's instead of H's. So I apologize for not having that. Okay. Now here are some equations that were also given. I just put them out here because I don't believe they're on your equation sheet. So I maybe recommend you writing them on your cheat sheet. But you were given a couple of equations. The first set is for the change of entropy of our surroundings. Okay, so whenever we have an exothermic reaction, right? Remember, that means that our system is going to be releasing heat into our surroundings. Okay, so our surroundings in terms of entropy, if it's gaining heat from the system, we are going to have an increase in entropy. Okay, and the increase in entropy of the surroundings, again, it's going to be positive, but it's going to be equal to the quantity of heat in terms of joules divided by the temperature, right? That's the magnitude. Okay, if it's an endothermic reaction where the system is taking away heat from the surroundings, if our heat of surroundings is decreasing, well, our entropy is also going to decrease. So our entropy of surroundings is going to be equal to negative the quantity of heat transferred divided by the temperature. Okay, now if these are done at constant pressure, the quantity of heat is going to be equal to delta H. Okay, now we have another relationship that says that the change in entropy of the universe is equal to negative delta G in terms of joules divided by the temperature. Okay, so again, I recommend you have these on your cheat sheet just because I don't believe that they are on the equation sheets. Now, the reason why I included these equations in this review, these are not typically equations very heavily used on exams. And honestly, I feel like this might be the first year, maybe second year that they bring these up. And if they have, they bring them up very transiently. They don't focus a lot on them. The reason why I think these are rather important, let me just go back to a slide. Is if you take this second law of thermodynamics, the change in entropy of the universe equals the change in entropy of the system plus change in entropy of the surroundings, and you apply these equations to that, you do substitution, you will end up getting this second equation for our Gibbs free energy, right? So those side equations kind of help us derive delta G naught equals delta H naught minus T delta S naught. Okay? And so I'm actually, because we're talking about it, just going to focus on this second equation first, right? So I'm sure by now we're very familiar with this equation and how Gibbs free energy relates to enthalpy and entropy. Really, the only thing I want to comment on about this equation, because again, we have used it so prevalently, is remember that delta H is usually given or calculated in terms of kilojoules. Well, delta S, our change in entropy, is almost always given in terms of joules per Kelvin. Okay, now the Kelvin portion cancels out when we multiply temperature. But the part that I really want to point out is delta H is in terms of kilojoules, delta S in terms of joules. Okay, and so when you actually do the subtraction between these different mathematical terms, remember to convert one of these variables, right? Convert them both to kilojoules or convert them both to joules. Okay, you can't take kilojoules and subtract joules from it and get the correct answer. You have to make sure that they're both the same unit. Okay. The other equation that we can use to solve for delta G is this equation. And you'll notice that it's very similar to how we solve for delta H and delta S, right? The change in Gibbs free energy is going to be equal to the sum of the Gibbs free energy of products minus the sum of Gibbs free energy of reactants. Okay, now the G naught F, that's the kind of formation value or the energy required to make 1 mole of each compound. These will be given in a table for you. Okay, now any element in its standard state will have a formation value equal to 0. Okay, and so if it's equal to 0, it's probably not going to be in the table. So again, if you feel like you're not given enough information in the table to solve for delta G through this manner, it's probably because that specific compound or element is in its standard state, thus its formation value is 0. Okay, before I move on, I think there was just a question. Somebody asked in the chat, is entropy sometimes given as joules per mole Kelvin, or is that something else? So to clarify, delta H and delta S are technically both given. So delta H would be given in kilojoules per mole, and delta S would be given in joules per mole Kelvin. Okay, the only relevance of that mole portion is that, sorry, let me backtrack. So for this equation, delta G naught equals delta H naught minus T delta S naught, you will typically be given delta H in kilojoules and delta S in joules per Kelvin. If you're using the top equation, right, your formation values in the table would be given in either kilojoules per mole or joules per mole. And the significance of when you see, kilojoules per mole or joules per mole is it just says that when you're doing these calculations, you have to account for the coefficients in the balanced chemical equation, right? So let's say the formation value for liquid water is 200 joules per mole, okay? And maybe in the balanced chemical equation, the coefficient for water is 3. Okay, when doing the calculations up here, I would have to do 3 times the formation value for water, which is 200 joules per mole. And so really it takes 600 joules to form those 3 moles of water. Okay, so whenever you see like moles in the denominator, it's really just telling you to multiply by the coefficient in the balanced chemical equation. Okay, and please let me know if that answered your question. Because you don't typically see kilojoules per mole or joules per mole Kelvin in this equation unless you're deriving delta H or delta S through an equation similar to this top one. Okay, perfect. Okay, so what's the significance of delta G or Gibbs free energy? Well, the significance is really the sign. Okay, if delta G is equal to 0, you are at equilibrium. Okay? If delta G is greater than 0, therefore it's positive, the reaction is not spontaneous. Okay? Now, if a reaction is not spontaneous, it can still occur, right? We can make it occur through applying external energy, right? So the classic way of doing that is maybe upping the temperature, right? That thermal energy will help a non-spontaneous reaction become spontaneous. Or we can couple an unfavorable or a non-spontaneous reaction with a favorable one, which really means we're going to have one spontaneous reaction, one not spontaneous reaction, and basically the energy released from the spontaneous reaction will allow the non-spontaneous reaction to occur. Okay, and then our last option is if delta G is negative, and in that case the reaction is spontaneous, and really the significance of that is a spontaneous reaction is just a reaction that doesn't require external forces to occur. Like it doesn't need additional heat or energy. Okay, now this is kind of a general chart for that second equation that I had for Gibbs free energy. So delta G naught equals delta H minus T delta S. This kind of shows you what signs for delta S and delta H, what they result in terms of delta G. Now, if you don't feel comfortable with these calculations and deriving this yourself, I would definitely recommend writing this on your cheat sheet. I think even just having it is really helpful. However, I don't quite remember what session it was, but I actually derived this chart in an SI session, and I definitely recommend as part of your preparations for this exam, kind of investigating these signs and the result on delta G. Because a very common question would be, based on the sign of delta S and delta H, is this reaction spontaneous? Or an even better question is, at what temperature will this reaction be spontaneous? That is a much better question. So just keep that in mind. Just quickly to talk about the manipulations for Gibbs free energy or delta G. We really in chemistry, or at least in Gen Chem, see three major manipulations to equations. So sometimes we might take the reverse of the equation. So instead of the reaction A to B, we might want B to A. So whenever we flip an equation, we're just going to change the sign on delta G, right? So instead of positive 10, it would now be negative 10. Okay, if we ever want to multiply a given equation by a certain coefficient, so maybe 3A goes to 3B instead of A to B, we're just going to multiply delta G by that same coefficient, right? So delta G here would be 30 kilojoules. And lastly, if we ever want to add two equations together, we would just add their delta G values together. Okay, and I saw there was something in the chat. Somebody asked, should we memorize its derivation? So I wouldn't say that you should memorize the derivation of this chart. Maybe this is what you're alluding to. I would recommend to understand how to derive it. Okay, so again, I would look at how I'm doing air quotes, derived it. I wasn't really deriving it. I was just saying, okay, let me plug in a positive S and a negative H value into my delta G equation. Okay, and then by looking at the signs, you can kind of come up with when will delta G be negative, therefore spontaneous. So I wouldn't say memorize the derivation. I would say understand how to derive it, if that makes more sense. Okay, and just two more slides on chapter 17. So how does pressure relate to these variables? So enthalpy, or delta H, is not dependent upon pressure, right? It is not affected by the pressure. However, entropy is, right? We previously said that entropy will decrease as pressure increases. And this is due to the relationship between pressure and volume, right? As volume increases, entropy increases, okay? And pressure and volume have an inverse relationship. Therefore, If pressure increases, entropy will decrease. If pressure decreases, entropy will increase. Okay, and then the last 2 points are kind of equations, and this is for the real change in Gibbs free energy for one gas or multiple gases, right? And so this is how Gibbs free energy is dependent on the amount of reactants and products we have, right? We're typically dealing with pressures here. We don't really deal with aqueous state as often. And so that's why you'll see kind of pressures down here. Okay, but if you're ever dealing with just one gas, which you don't typically see, but I would definitely have this equation down just in case you do see it. The equation for this is that the change in Gibbs free energy is equal to the standard Gibbs free energy for that gas plus R, our constant, it's going to be 8.31 joules per mole K, times our temperature, times the natural log of the pressure of that gas in atmospheres. Okay, now what I'd expect to be more likely seen on the exam is this second equation, where you have multiple gases, and so you're going to be using your reaction quotient, or Q. Okay, but you'll notice that that's really the only difference between the top equation and the bottom equation. Okay, so again, reaction quotient Q will be used there. And how does this relate to equilibrium? So it's really important to remember that at equilibrium, delta G is always equal to 0. And so if we would manipulate the equation we were just looking at, right, delta G is 0, so we plug that in, and we change the variables around, and what we find is that the standard change in Gibbs free energy will be equal to negative R times T times the natural log of K, right? We're going to insert our equilibrium constant, or K, in here instead of Q, because we are at equilibrium, right? So it's just proper to write K here. Okay, and kind of our final equation that I just didn't really have a spot for. It's a combination between the two equations listed to the right. And so it's the natural log of K is equal to the negative change in enthalpy divided by R times 1 over temperature plus the change in entropy over R. Now I could really only see this appearing as one multiple choice question, and how I think it would appear, or how it would likely appear, is that you would graph the natural log of K on the y-axis, and 1 over temperature would be your x-axis. And the significance of this is that the slope, a linear slope would result, and the slope would be equal to the, and don't miss this, it's a negative, the slope is equal to negative delta H over R, which is at 8.31 joules per mole K value, and the y-intercept would be equal to the change in delta F, or delta S divided by R. Okay. Okay, so that concludes our review of chapter 17. Are there any questions before we jump into chapter 18?
I have a question.
Yes.
So when you're say they give you a question on like change in S, and how would you differentiate, like say they say like, oh, which process has a negative change in S value, and they give you like equations, chemical equations with the like state, how would you differentiate which one would be negative if they just give you the equation?
So sorry, you said their state. So do you mean if they give you a chemical formula with, you know, the classification, so solid versus liquid versus gas, like if they just give you that equation, how do you tell which side or what's the sign of delta S is?
Yeah, so if they give you like 4 choices and 4 different chemical equations with each compound state, how can you tell which option has a negative change in S?
Yeah, good question. So what I'd say is if they ever have you do that, it's going to be pretty obvious, meaning it's going to, I went through 4 or 5 trends.
Mm-hmm.
They would comply to those trends. Because entropy can be very complicated. And so if it's kind of ambiguous which side might have higher or lower entropy, they would give you a table of values so you could actually physically solve that out. In terms of your question, if they give you 4 equations and ask which one has a negative delta S, what I'd recommend you do is take each one of those individually, look at the reactant side and look at the product side, and look at those 5 trends that I listed and ask yourself which side has a higher amount of disorder or entropy. And you would list, okay, maybe for A, B, and D, the product side based on those trends should have higher entropy. But for C, based on those trends, the reactant side would have higher entropy. And so based on that, you would be able to find out that it would be, your answer would be C, that has a negative delta S.
Okay, because the reactant side would have higher entropy.
Yes.
Okay, all right, thank you.
Yep, you're welcome. And it's pretty long ago. I remember one of my challenge problems when we went through thermochemistry was doing that. I believe it was with the cellular respiration equation. And so, or even really any of Dr. S's examples, really just, if you're ever in that circumstance, you should really separate each choice from one another and look at them each individually, compare reactants to products, and use those 5 trends, okay? Because if they don't conform or comply with those 5 trends that we know for entropy, then we don't really have any way of truly knowing what the delta S is. And so therefore, they'd have to give you values to actually calculate it. Okay. Are there any other questions before jumping in? I'm also happy to stay at the end and answer questions for as long as is needed. Okay, so for the most part, these are going to be review from Monday, so I'll kind of go through electrochem a little bit more quickly, but the last 3 topics or so are new, so we'll spend a little bit more time on them. Okay, so just some terminology for electrochemistry. So remember, oxidized and reduced. So oxidized means that that element has lost electrons, and it will increase in oxidation number, which in this chapter we typically see as an increase of charge on a specific element, right? Reduced means that that element gained electrons, okay, which means it will decrease in oxidation number. And again, in this chapter, typically means that it will decrease in its charge on the element, okay? Now remember, oxidizing versus reducing agent, okay? Now, the fact that they're a reactant isn't that applicable to this chapter, okay? But remember that the oxidizing agent causes oxidation by getting reduced, okay? So the oxidizing agent actually is getting reduced, okay? And the reducing agent is actually getting oxidized, okay? That's an important distinction. Okay, and I show an electrochemical cell in the next slide, but just to talk about the components. So we have 3 main components that are important. We have the salt bridge that combines our 2 electrodes, and the salt bridge allows for the exchange of ions or ion movement. And the importance of this is the movement of ions allows charges to balance. And you need charges to balance because electrons are transferring from one end to another due to the redox occurring. Okay, there'll also be a metal wire, and this allows electrons to move. Now it's important to note that electrons always move from anode to cathode. Okay, and that's kind of one of those not weird points, but that's one of those points that tends to show up a lot on these exams as part of one multiple choice question, right? That's something they like to include in like a true false question. So remember that electrons will always flow from anode to cathode. Okay, and then we have 2 electrodes, right? We have our anode portion, which is where our oxidation occurs, and then we have our cathode electrode, which is where our reduction will occur. Okay, and so this is just a general picture of an electrochemical cell. So we have an anode here, right? You typically have like a metal bar and a solution in both your anode and cathode. But remember, anode is where oxidation occurs. Oxidation is loss of electrons. Okay, so electrons are lost here, and those electrons, when they're lost, travel around the wire to the cathode where reduction occurs, hence electrons gained, reduction. Okay, now we have two types of cells, right? We have spontaneous electrochemical cells that have a positive E value and non-spontaneous electrochemical cells, which have a negative E value. Okay, now spontaneous electrochemical cells can go by one of two names in this course. We call them voltaic or galvanic cells. Okay, they are interchangeable. Voltaic or galvanic are spontaneous electrochemical cells. Electrolytic cells are non-spontaneous electrochemical cells. Okay, and these require or use electrical or heat energy to push a reaction against the gradient, right? It's unfavorable, so it needs an input of energy to be favorable or to occur. Okay, and the process of this is called electrolysis, right? The process of pushing an unfavorable reaction forward by using electrical power, right? So an example of a voltaic and galvanic cell would be a battery, right? It has a cathode and anode that go along its natural gradient to produce electrical power, which causes your devices to work. An electrolytic cell would be like your phone charging at night, right? Maybe your phone battery's dead, you plug it into the wall, and so it's using outside electrical power to push your phone battery against its natural gradient, causing it to recharge, right? It's kind of going the reverse direction by using outside energy. And so the driving force behind these cells is E, our cell potential. And so this cell potential is equal to the sum of half reactions. Okay, so we're going to add our reduction half reaction or our reduction potential plus our oxidation potential. Okay, and I got an email or two about this today, and so I wanted to specify, because this is actually something that's come up almost every year, people are confused about. So there's two different equations that you can kind of use to solve for the reduction potential or the cell potential, right? So there's this one that I use, and this one will get you the correct answer, right? It's the cell potential of the reduction half reaction plus the potential of the oxidation reaction. Okay, the key to this, and I have an example that we've done before on the next slide to show this, the key to this is our oxidation half reaction, we're actually going to flip it, okay? And when we flip that reaction, we change the sign on E to put it in terms of oxidation, and then we add these two together to get our cell potential. Now the other equations, which I find to be slightly misleading, and this is what I got emails about, some of you may have seen in discussion. And so you may have seen that the cell potential, standard cell potential, is equal to the potential of the cathode minus the potential of the anode. Okay, and we know that at the cathode reduction occurs, and at the anode oxidation occurs. So you can kind of get this top equation. Now I find this to be kind of misleading, because again, it looks the same as above, but it's not. And the reason for this is if you use these bottom equations, you will still get the right answer. Okay, but when you plug in these values, you're plugging them both in terms of their reduction potential. Okay, so this E naught oxidation, you are not flipping that half reaction. Okay, you are just plugging in the reduction potential of the cathode reaction, subtracting from it the reduction potential of the anode half reaction. Okay, whichever one works for you is perfectly fine. I, over the past 5 years, have just always been drawn to this top reaction and that process. It's made more sense to me, but again, either will get you the correct answer. And so here's an example we did at last SI, right? And so it's a spontaneous cell. Here are our two half reactions. And so I solve it using both methods. Okay, so because this is a spontaneous cell, it has to have a positive E value. Okay, and so that indicated to me that I had to flip my potassium half reaction, so I did that. And you'll notice when I flipped my potassium half reaction, I actually, I put the oxidation potential here, and I changed the sign, right? It's no longer negative 2.9, which was the reduction potential of potassium plus. It's the oxidation potential of potassium solid. And so it's now a positive value. So now that I have my equations in terms of oxidation and reduction, I add these two values together and get my cell potential. Now the other method, right, we're going to write these two equations, and you'll see that we kept the potentials in terms of reduction, right? So the potassium equation is negative 2.9 volts. Okay, now through this method, you have to kind of realize that the potassium equation is the one that should be oxidized, and the chromium one's the one that should be reduced. Okay, so the oxidized reaction, the potassium occurs at the anode, while the reduced element, chromium, occurs at the cathode. And so we take our equation, the cell potential is equal to the potential of cathode minus the potential at the anode, and realize that we plug in the values here in terms of their reduction potential, and we get the same answer. Okay, and so whichever method makes more sense to you, feel free to use. I just have always liked the top reaction or the top method much more, where you just flip the oxidation half reaction around, change the sign, and add them up. Does that make sense to people? I got a couple emails about it today, but again, I know that's something that has really confused lots of students, including myself and peers when I took this course. So does that make sense now that I maybe explained it? Hopefully. Awesome. Thank you, Victoria. Okay, so here's just some manipulations of reduction potentials or cell potentials, which is our E values. So if you ever flip a reaction, which I kind of just showed you before, right? If you ever flip a half reaction or a full reaction, you're just going to change the sign on E, right? So if it was positive, it's now going to be negative or vice versa. If you ever multiply a half reaction by a coefficient, right? And this is really important. People often forget this. There is no change on your reduction or cell potential. Okay, you do not multiply E by that value. Okay, and if you ever have to add equations together like we do for our half reactions, you just add those E values together. Okay, and if you didn't see Monday's SI, I'd recommend you go and watch a portion of it. I actually have this, what I find to be a very useful chart that compares our manipulations for K, equilibrium constant, delta G, Gibbs free energy, and E. Because we've learned these three manipulations for all three, and they are different from one another. So kind of having a chart to show the difference that you can reference whenever you need, I think can be pretty beneficial. Okay, these couple of equations really just relate cell potential to Gibbs free energy and equilibrium, right? So delta G naught is equal to negative NF E naught. So N is how many electrons are transferred in our redox. F is Faraday's constant. E naught is our standard cell potential. And then the bottom two equations are kind of the same. It's to solve for standard cell potential. And it's equal to RT over NF times the natural log of our equilibrium constant. So all the variables are listed below. This number, 0.0257, is achieved by taking the R constant, dividing it by Faraday's constant, and multiplying it by the temperature when you're at 25 degrees Celsius. So it's 298 Kelvin. Okay, these are extremely important equations, and I would expect you to use them multiple times on this multiple choice exam. Okay. And then lastly, of things that we kind of reviewed last time before jumping into the new material, it's our Nernst equation. Okay, and so this allows us to solve for the real cell potential when we're at temperatures other than 25 degrees Celsius and when we're not necessarily at, equilibrium or standard states. Okay, so we're just going to quickly kind of touch upon three new topics. They're not typically the most heavily tested upon. I think units in electrochemistry does appear a little bit. And so here they are. I really don't have much to talk about in reference to them. So we have a Coulomb, which is really just a measurement of electrons, so charge. So 1 mole of electrons is 9.648 times 10 to the 4th coulombs. You'll notice that that actual value is pretty similar to, it's like Faraday's constant, or at least the magnitude of it is equal to Faraday's constant is what I should say. I would say the biggest takeaway from all these different units in electrochemistry is the actual units that they're equivalent to, right? So understanding ampere is coulombs per second. Volts is joules per coulombs. Watts is joules per second. Joules is volts times coulombs. I think by kind of doing unit analysis in these problems, that's really the best way to go about these. And so here's a little chart that your professors gave you. And so this is kind of what they represent in electrochemistry. So charge, the unit for charge is coulomb. Whenever you're talking about current, and you'll see this when you take physics, or if you've taken physics in high school, right? We measure current in terms of amps or ampere. Potential is volts, power, watts, energy, joules. Again, the relationships, so these are what we had on the last slide. And then these are some really important conversion factors that you may need to use in calculations. And so this general chart I would recommend you have on your cheat sheet. Again, the extent that they ask you about units in electrochemistry on the exam, it's typically a pretty minor part of the exam. Maybe 1, maybe 2 questions, if that. And so really, I think just having this chart and working through your units is kind of the best bet. And so let's look at one quick example. So 100 grams of chromium undergoes reduction according to the reactions below. And this occurs over 2 minutes and 15 seconds. What amount of amperes is associated with this reduction? Okay, and so we're talking about chromium. And so this top reaction we actually don't care about. It's chromium 3+, reacts with 3 electrons to produce a chromium solid. Okay, and my suggestion for this is what I was talking about, how units are what kind of matter. Is right, we're being asked for amperes. And so when I look at that chart, I can see an ampere is coulombs per second. And so what I would personally do myself for a problem like this on an exam is I would separate, or I'd kind of divide my numerator and denominator and work on them separately. Okay, so to solve for amperes, right, I'm going to first focus on my denominator, which is seconds. So for this part of the problem, right, how many seconds over did this occur over? And so it occurred over 2 minutes and 15 seconds. And so I can convert this and find that this reaction occurred over 135 seconds. Okay, so that is my denominator number. Okay, so now let me focus on my numerator, coulombs, right? Well, coulombs are really, it's an amount of and it's the amount of electrons transferred. So I'm going to get it from electrons. So if I had 100 grams of chromium, 1 mole of chromium is 52 grams. And from my half reaction, I could see that 1 mole of chromium, 3+, or just chromium, right, is associated with 3 electrons, right? Let me go back. See, 1 mole of chromium 3+ is associated with 3 electrons. Okay, so that's how I get that conversion. And then 1 mole of electrons is this 9.648 times 10 to the 4th coulombs number. And so by doing that dimensional analysis, I can find that 100 grams of chromium is associated with 5.566 times 10 to the 5th coulombs. Okay, so as you can see, I solve for my numerator and denominator separately. And so now that I have coulombs and seconds, I can find amperes by just taking my number of coulombs, dividing by seconds, and I get a little over 4,100 ampere. So again, in these types of problems, I would kind of recommend separating your units and kind of almost dividing and conquering these problems. Okay, the last two slides I have are just to talk about the last two videos for this chapter. And the first one is electrochemistry in water. Okay, and so water can also be oxidized and reduced, which actually kind of complicates the chemistry that is undergone. Okay, so we're going to look at the two electrodes separately. So again, we have our cathode and our anode. So our cathode is where reduction can occur, or it does occur. And so we can either reduce our respective half reaction, or we can reduce water to hydrogen gas and hydroxide. Okay, now the value, the reduction potential for water being reduced is negative 0.828 volts. Now I would expect you to be given, this is a topic that I haven't seen covered really in the past. So they would definitely give you this value. Okay, and the important thing is to compare this value to the reduction potential of the half reaction that you're trying to reduce. Okay, and so if your half reaction, or for any half reaction with a reduction potential, right, greater than this value, meaning more positive, okay, so the actual number might be smaller, but it would be a smaller negative number. Okay, so if your reduction potential is more positive than the reduction potential of water, then your half reaction will be reduced. Okay, now if the reduction potential for a half reaction is more negative than the reduction potential of water, then the water will be preferentially reduced instead. Okay, so your half reaction would not undergo the redox. It would be water that does it instead. Okay, and when this occurs, you will actually produce hydroxide, making your conditions alkaline or basic due to hydroxide production. And when this occurs, you actually need to use a slightly different chart that is based on a basic environment, right? Dr. P mentioned that. Okay, now this can also occur at the anode. So at the anode, oxidation occurs. So instead of our half reaction being oxidized, water could be oxidized to oxygen and protons. Okay, and so the reduction potential, or sorry, so realize that the water is being oxidized. Okay, and so on the chart, which is always given in terms of reduction potential, the reduction potential would be given as 1.299. But again, it's being oxidized. So the oxidation potential would really be negative 1.299. Okay, and so the key points for this is any half reaction with and I'm putting this in terms of reduction potential because that's how the chart is laid out with, any half reaction with a reduction potential that is more positive than the reduction potential of water being oxidized, then water would preferentially be oxidized instead of the half reaction. Okay, on the contrary, if the reduction potential of the half reaction is more negative, right, so less than 1.299, or more negative than the water's potential, then the half reaction will undergo oxidation. Okay, and so I really recommend also having this on your cheat sheet. And I would say also look at the second to last lecture video as well. I think looking at the visuals that Dr. P provides along with these bullet points can really help make sense of what this is trying to say. Okay, and if you take a step back and actually look at this in general, these trends make sense, right? Because large negative numbers are hard to reduce, right? You don't want to reduce them. You'd prefer to oxidize them. And the reason for this is if you're oxidizing it, you're actually changing the sign on this large negative number, making it a large positive number, which helps the reaction be spontaneous, right? Large positive reduction potentials are hard to oxidize. They prefer to be reduced because large positive reduction potentials are already well on their way to being spontaneous. Okay, sorry, this is the last slide. I know I've gone quite a bit over. So the last lecture video talks a bit about corrosion. And so the first part was talking about rust, which is the oxidation of iron. This process is accompanied with the reduction of oxygen. And it's also accelerated by salt on the road, right? That's why we actually see a lot more rust. I actually had to hear my mom talk about my dad's truck rusting, relatively new since we got it, because we live in New England, right? We have to put a lot of salt on the road to prevent freezing, but that salt acts as a salt bridge between our oxidation and reduction reactions seen. So we see a lot more rust on our cars. Salt also allows stable chlorine complexes to form that also facilitate this process. Now, I think the part that maybe could come up on the exam or has a higher chance of coming up on the exam from this last video is ways to prevent corrosion. And so 3 different ways to prevent corrosion were talked about. The first is through a surface passivation layer. Okay, and this occurs where a surface oxide with a density equal to the underlying metal layer is formed. Okay, so maybe the metal that we're trying to protect is solid silicon or solid aluminum. And so what will occur is we will make a layer or have a layer of silicon oxide, right? So a layer that is oxidized that will lay on top of our pure silicon or pure aluminum, and it will protect the layer underneath from being oxidized. Okay, so as you can see, it's an already oxidized layer on top of the metal that's protecting it. The other method is through, or the second method is through galvanization. And here we're going to apply a zinc coating over either steel or iron metal. And the reason we do this is that the oxidation potential of zinc is greater than the oxidation potential of iron and steel. Therefore, zinc will preferentially oxidize, and this will protect the steel or iron metal underneath from oxidizing. Okay, and this may occur through zinc providing This may occur through zinc providing electrons to the iron or steel. That portion of it I wasn't the most, confident in. Based on what Dr. P was saying, it kind of confused me. Originally, I interpreted it as the zinc gets oxidized and therefore the outer layers oxidized, therefore protecting the inner layer. He kind of more made it seem like electrons from the zinc are kind of preventing the iron or steel from being oxidized. So you could, if that confuses you too, you could reach out to a professor. They would have a better idea. The last way to prevent corrosion is very similar to galvanization. It's called sacrificial anode. Okay, and so here we're going to use a metal that is more reactive. And so in an example, we might use magnesium. And by more reactive, we're saying it has a higher oxidation potential. Okay, and we will have an electrical connection for this metal to another metal that we're trying to protect. So maybe iron metal. And what will happen is this magnesium will actually preferentially and purposefully become oxidized. Okay, and while magnesium gets oxidized, the electrons will transfer along the electrical connection, and that input of electrons will actually prevent the iron from getting oxidized. Okay, so that's the final point I have. So at this point, I'm happy to answer any questions. The last thing I really want to say is I actually do not have any challenge problems prepared for tonight. I got my second COVID vaccine on a couple hours before Monday session. So I felt good to do Monday session, but I was feeling pretty ill yesterday. So I really wasn't feeling up to making those problems. So I will really work as hard as I can tonight to get as many problems as I can done. I'm really hoping to have between like 10 and 14 questions, about 5 to 7 per each chapter, all multiple choice prepared. And I will look to get those problems up and a session going over those problems up as soon as I can when I remember, I do have a full-time job during the day. So I will work as hard as I can to get those up as soon as I possibly can. But I do not yet have them prepared. So hopefully by tomorrow around 5, 6 p.m., those will all be up, but I will do my best to do that. But I'm just gonna end the recording here, but if there are any questions, I'm happy to answer anything.